Okay, so let's derive the method for least squares regression. And sometimes this is called ordinary least squares regression. And that's because there are other types of least squares regressions. One being robust least squares regression, which controls better for outliers in your data, or it lessens the importance of outliers on your data. And I might do that in another video. So for ordinary least squares regression, let's say that we have some data and it's two-dimensional. So we have a set of points and we want to fit a line so we have a set of points and we want to fit a line to that data. So we'll call this y equals mx plus b. We want to fit a line to that data such that the sum of the squares of the distances of each point, so these distances, the sum of the squares of those distances is minimized. So what we want to minimize we'll call r squared, the residual, and we'll call it squared because we might wish to square root that. And that's going to be the sum over I equals 1 to n. So say we have n data points, and these are pairs xi comma yi. So we're going to sum the squares of the error. So the error is going to be the difference between the actual y value and our model. So the value of our model is what we get when we plug xi into the model. So it's minus mx plus b. And we're going to square those. So if you square root both sides, then we can think of the residual r as the sort of like the Pythagorean length of the error. We sum the squares and then we square root it. Or the mean squared error. And let's go ahead and just expand this square to make it easier to take the derivative. So we have yi squared, we have minus 2 times the product of the first two terms, and we have, well, plus 2 times the product of the first two terms, plus 2 times the product of the first and third, and plus 2 times the product of the last two terms. And then we have the squares. So we have m squared xi squared plus b squared. Okay, so now we're going to take the derivative, but remember we have two variables, m and b, that we can change to optimize this model. So we have two variable optimization. So first let's take the derivative of r squared with respect to m. And we don't have to worry about the chain rule with r squared or anything, just treat it as its own variable. And so by linearity we can just distribute the derivative straight through the sum. Well, the yi squared goes away because those are just numbers, they're constants. We have minus 2 xi yi because we have that m term. Next term 0, and then we have 2bxi because b is a constant, and then plus 2mxi squared. And we're going to set this equal to 0 by definition of optimization. And we can go ahead and just divide through by 2. Since 0 divided by 2 is 2. And before we try to solve this further, let's go ahead and take the other derivative. With respect to b. So first term 0, second term 0. We have minus 2yi plus 2mxi, and then 2b. And again, that's defined as 0, divide through by 2. And so now we actually have a system of equations for b and m. So let's go ahead and simplify this so that we can see the coefficients of m and b. So for the first equation, the coefficient of m is sum of xi squared. And just for simplicity, I'm going to leave the indexing off because we know it runs from 1 to n. So the sum of the squares of the x values is the coefficient for m. And then just the sum of the xi values is the coefficient for b, and we'll move that other term onto the other side, which is the sum of xi, yi. And then for the other equation, the coefficient for m is the sum of the xi values, and the coefficient for b is just the sum of 1's. Well, if we add 1 up n times, we just get n. And then the coefficient we move to the other side is the sum of the yi's. So now we have a matrix equation times our vector mb and our coefficient vector and so now we'll take the inverse of that matrix, and in a second we'll show that it is in fact invertible. So to solve for MB, we invert that matrix, and to invert a 2 by 2, we just switch the elements on the diagonal, and we negate the elements on the off diagonal, and then we divide by the determinant, which is the first term times the fourth term minus the second term times the third, but they're the same. And then we're going to multiply that by our coefficient vector. And so now just continuing to solve this for m and b. For m, we're going to have n times the sum of xi, yi minus the sum of xi times the sum of yi all over this determinant, and for b we get all over And so these are the parameters for your linear model in order to minimize the error. So this is the best linear model for data with a perceived linear correlation in the least squares sense. So how do we know that this is actually a minimum and not a maximum of the error? Well, we just need to do the second derivative test. So the second derivative test for two-dimensional optimization is if the determinant of the Hessian is greater than 0, the Hessian is the second derivative matrix, and the first element is greater than 0, then we have a local minimum. So we just need to find the Hessian and take its determinant, show that it's greater than 0, and then we need to check that the first element of the Hessian is greater than 0. So grabbing those first derivatives again, we need to solve for our second order partials. So the second derivative with respect to m is just 2xi squared, and the second derivative with respect to b is just 2, the sum of 2, which is 2n. This one we can factor out the 2. And then, since these are continuous functions, then the two mixed order partials are the same, which you can verify. So let's just take the derivative of the one with respect to m, but now with respect to b. So we're going to get 2xi here, and factor out the 2. Okay. And so the determinant of our Hessian's going to be 2 sum of xi squared, 2 sum of xi, 2 sum of xi, and then 2n, which is going to be 4 times sum of xi squared times n minus the sum of xi squared. So ignoring the 4, this expression is greater than or equal to 0 by the Cauchy-Bunyakovsky-Schwarz inequality. Sometimes Bunyakovsky is included. I'll prove this one in a different video, but basically what it says is that the inner product, which a dot product is an example, of two vectors is less than or equal to the product of their magnitudes. And we get equality only if one vector is parallel to the other. And we're just going to use the square of both sides of the Cauchy-Schwarz inequality. So this just says that the dot product, the vector that we'll use is a vector full of 1's, and the other one is just our xi values, so x1 through xn. If we take that dot product and square it, that's going to be less than or equal to the product of the squares of the norms of each of those vectors. So this term on the left, if we just take the dot product here, we're just going to get the sum of all the xi values squared. The norm of a vector full of 1s is just the sum of the squares of 1, so this is just n. And then the norm of the xi vector, well, that's just the sum of the squares. The norm squared is the sum of the squares. So if we don't square root that. And so we see that the second term is less than or equal to the first term, and so that's greater than or equal to 0. And the other part of the Cauchy-Schwarz inequality is that we get equality if and only if our two vectors are parallel. But these two vectors can only be parallel if xi is some multiple of this vector f1's. Which means that each element is the same. They're all the same number. So that would mean all of our xi values are the same, in which case we just have a horizontal line and we don't need to do a regression at all. Okay, so since we don't have that all of the xi values are the same by assumption, then we don't have equality. We have a strictly greater than here, which meets the first condition of the second derivative test, and the second condition is just that the first term is greater than or equal is greater than 0. Well, since they're all positive, by assumption, if all of the xi values were a 0, again that would just be a horizontal line and we wouldn't need regression, and so we're assuming this number is strictly greater than 0, and therefore we have a maximum. And that's all. Thanks for listening. Let me know what else you'd like to see. Like, subscribe, leave a comment, and make sure to check out westworks47.com for tutoring and applied math consulting. And just a quick side note, the Cauchy-Schwarz inequality is easy to see if you look at the dot product formula. So at least for the dot product, we have that the dot product is the product of the magnitudes times the cosine of the angle between them, and cosine of theta is less than 1 unless theta is 0. In other words, the two vectors are parallel.